This is a lesson 15 supplement. It's related to spectator ions. And there's three types of spectator ions: acid-base, precipitation or solubility, related, and redox. The most common of these are the group 1A, which includes sodium ion, potassium ion, rubidium ion, and cesium ion. All three of these cases, the alkali metal cations, are spectators. Others could precipitate out. Other ones could have redox properties, i.e. they could reduce or oxidize. So let's look at a simple calculation that gives us an idea about why these are spectator ions. Let's take, for example, sodium ion hydrolyzing the water molecule. Remember, that's splitting it apart. And I'm going to go ahead and put the arrows in that direction. So then what I have then is I get sodium hydroxide plus hydrogen ion, which is a strong acid, strong base. So we would suspect that the equilibrium, in fact, lies to the left, favoring the reactants, i.e. sodium being a spectator ion. Well, this is a Lewis acid. It can accept an electron pair. It's also an indirect Arrhenius acid because I could produce hydrogen ion, i.e. and I'm also ignoring sodium hydroxide here. Strongest acid in water in an aqueous system is hydrogen ion. Strongest base is the hydroxide ion. So we're assuming that sodium hydroxide in this case is an ion pair. It's stuck together. Okay, so let's look at that. Let's look at the K equilibrium constant for this guy. What do I have? I have hydrogen ion. I have hydroxide concentration as the ion pair over sodium. The reason why I ignore the water molecule in this equilibrium expression because it's a liquid, number one. And number two, it is a constant, 56 molar. So it doesn't change much. So what is this related to then? It's actually related to the Kw divided by the Kb, because the Keq in this case is Ka, because sodium ion's acting as a acid. Okay, so what do I have now? I have, the fact is, (10 to the minus 14 is the Kw value. And if I look up in my tables for the Kb value for sodium hydroxide, it's 10 to the fourth. That means my equilibrium constant for sodium ion act as an acid is 10 to the minus 18. Okay, at 298 K. Let's check that out. Let's see if my Ka is related to that, what I just said, right? 10 to the minus 18. Simple derivation would be, is my Kw is hydrogen ion times hydroxide ion. That's its equivalent. Again, I don't show the water. Now I'm dividing by what? The Kb. Well, the Kb reaction is related to sodium hydroxide acting as a base, which means I'm using the reciprocal of that, i.e., let's show that. Okay? So I want to take products over reactants, but I'm actually taking reactants over products in this case because of the fact is I'm using the reciprocal Kb. This is the Kb reaction. Therefore, I got sodium hydroxide over, ooh, got a little sloppy there, sodium ion times hydroxide. Notice the hydroxide cancel out. So did I just prove this relationship Ka is equal to that? Yeah, basically.